What if the most profound secret of our universe wasn't hidden in the depths of a black hole or the birth of a galaxy, but was, in fact, hurtling right through our cosmic backyard? Imagine a mystery so compelling, so riddled with anomalies, that it forces us to question everything we thought we knew about our place in the cosmos. This isn't science fiction. This is the true story of 3I Atlas, an object that appeared from the interstellar void, challenging scientific dogma and igniting a global debate. Buckle up, because we're about to embark on a journey that will unravel the curious case of the universe's most perplexing visitor. And by the end, you might just find yourself looking at the night sky with an entirely new perspective. In the vast, silent expanse of space, there are moments that transcend the ordinary, events that prick the ears of even the most seasoned astronomers. July 2025 delivered just such a moment. From the high-altitude observatories of Chile, the Atlas telescope, a sentinel gazing into the cosmic ocean, detected a fast-moving object. It was initially just a blip, a fleeting signal, but within days, its significance became undeniably clear. This wasn't merely another asteroid or comet. It was something far more extraordinary. It was designated 3I Atlas, marking it as only the third confirmed interstellar object ever detected passing through our solar system. Now, for those of us who aren't fluent in the language of astrophysics, an interstellar object is precisely what it sounds like: a visitor from another star system, traversing the immense distances between galaxies. These aren't common occurrences. Think of our solar system as a tiny island in a vast cosmic ocean. For an object to drift from another island and happen to pass so close to ours is akin to throwing a message in a bottle into the Atlantic and having it wash up precisely on your doorstep in a specific bay. It's an incredibly rare event, making 3I Atlas inherently fascinating from the outset. But as astronomers began to meticulously plot its course, the fascination quickly morphed into bewilderment. Its trajectory, the path it carved through the tapestry of our solar system, was, to put it mildly, bizarre. It wasn't a random, chaotic tumble. Instead, it was unusually aligned with our solar system's ecliptic plane, the relatively flat disk in which all our planets orbit the Sun. Even more peculiar, it was slated to pass tantalizingly close to not just one, but three of our planetary neighbors: Mars, Venus, and Jupiter. The statistical probability of such a precise alignment occurring purely by chance? Vanishingly, almost impossibly, low. It was as if the universe itself had meticulously orchestrated a grand cosmic flyby, tailor-made for our observation. This wasn't just a visitor, it was an appointment. This initial anomaly was just the first thread in a rapidly unspooling tapestry of cosmic intrigue. When the venerable Hubble Space Telescope, humanity's watchful eye in orbit, turned its gaze upon 3I Atlas, it revealed something truly unexpected. Instead of the diffuse, dusty tail characteristic of a typical comet, Hubble images showed an unusual forward-pointing glow. Imagine a headlight on a train rather than the exhaust plume behind it. This wasn't a subtle difference. It was a fundamental departure from expected cometary behavior, immediately raising a forest of questions in the minds of scientists. Comets shed material as they approach the Sun, creating a tail that trails behind them. A glow at the front? That was unprecedented. What could be causing such an anomalous emission? As if Hubble's revelations weren't enough, the James Webb Space Telescope, with its unparalleled infrared vision, provided an even more startling piece of the puzzle. Webb observations showed that 3I Atlas was composed of an astonishing 87% carbon dioxide. Now, while carbon dioxide isn't unheard of in comets, such a dominant percentage is extremely rare. Most comets are rich in water ice, along with various other volatile compounds. A predominantly CO2 comet from another star system immediately suggested an origin in a vastly different environment than our own solar system's comets. It hinted at a formation process under conditions we might not fully understand, perhaps in a colder, denser region of space, or even within a protoplanetary disk around a star with a very different chemical makeup than our Sun. This wasn't just an oddity. It was a chemical fingerprint pointing to an unknown cosmic birthplace. The anomalies continued to pile up, each new observation adding another layer to the enigma. Spherex data, utilizing powerful infrared spectroscopy, suggested something truly colossal, a massive 46-kilometer diameter. To put that into perspective, that's roughly the size of a small moon. This made 3I Atlas potentially 1,000,000 times more massive than previous interstellar objects like Oumuamua or Borisov, 1,000,000 times. The statistical improbability of the third interstellar object ever discovered being so disproportionately gargantuan, defying all expected size distributions for natural objects, was staggering. It was like finding a single grain of sand on a beach that weighed more than all the other grains combined. Such a massive object traveling through interstellar space would have to be incredibly resilient to the cosmic radiation and collisions it would undoubtedly encounter over eons. Was it a single, solid entity or something else entirely? The sheer scale of it sent ripples of disbelief through the astronomical community, and the plot thickened further. The Very Large Telescope, VLT, another ground-based giant in Chile, detected nickel without iron in its plume. For those not steeped in geochemistry, nickel and iron are often found together in cosmic objects, especially in the cores of asteroids or remnants of planetary formation. To find nickel without its usual companion was another chemical head-scratcher, suggesting an unusual composition or a highly differentiated object. It implied a process that selectively ejected nickel, or an object formed from a unique brew of elements. This wasn't just a comet behaving strangely. It was an object with an alchemical signature unlike any we'd seen. Finally, just when scientists thought they had cataloged all the peculiarities, amateur astrophotographers, with their keen eyes and dedicated backyard observatories, contributed another perplexing detail. Their photos consistently showed a distinct green glow, despite spectroscopic analysis indicating a depletion of carbon chains, which are typically responsible for such a glow in comets. It was a contradiction, a visual paradox. The green glow, often associated with diatomic carbon, C2, in cometary atmospheres, simply shouldn't have been there in such prominence given the chemical readings. This wasn't merely a subtle variance, it was a glaring inconsistency between observation and expectation, pushing the boundaries of what we understood about cometary physics. Each of these observations, individually compelling, collectively painted a picture of an object defiantly refusing to conform to typical cometary classifications. It was a cosmic rebel, a rule breaker, a mystery wrapped in an enigma, cloaked in a brilliant, forward-pointing glow. By late September, Earth-based observations became increasingly difficult as 3I Atlas continued its journey. The stage was set for a dramatic climax, a close flyby past Mars on October 3rd. 7 orbiters, a fleet of robotic eyes and ears circling the red planet, were perfectly positioned to observe this pivotal event. This wasn't just an opportunity, it was a necessity. The Mars flyby was crucial, the last best chance for definitive answers to the myriad questions swirling around 3I Atlas. The scientific community held its breath, poised on the brink of what could be the greatest discovery of our time. Little did they know, a different kind of silence was about to descend, one far more perplexing than the vacuum of space. Isn't it fascinating how a single object can unravel so many assumptions? When you encounter something that defies all logical explanation in your own life, how do you react? Do you seek conventional answers, or are you open to the possibility that sometimes the universe or life throws us curveballs that force us to rethink our entire framework? Just as anticipation reached fever pitch, a mere 2 days before the critical Mars flyby, an unforeseen event plunged the scientific community, and indeed the world, into a frustrating information vacuum. The U.S. government, caught in a familiar partisan gridlock, shut down. This wasn't just a bureaucratic hiccup. It was a hammer blow to transparency, halting NASA's public operations and furloughing the very personnel who would normally process and release the invaluable stream of images and data from the 7 orbiters poised to observe 3I Atlas. The timing couldn't have been more agonizingly precise, arriving just as humanity's most advanced robotic probes were about to get an unprecedented close-up look at the cosmic enigma. Imagine being on the cusp of a groundbreaking discovery, only for the lights to suddenly go out. This wasn't a technical glitch. It was a human-made barrier, a wall of silence erected by political circumstance. The public, ravenous for information about this mysterious object, was left in the dark. While the European Space Agency, ESA, operates independently of the U.S. government, and their Mars Express and ExoMars Trace gas orbiter valiantly continued their observations, their contributions, while appreciated, were insufficient to quench the growing thirst for clarity. When their images were finally released on October 7th, they showed only a frustratingly fuzzy white dot. The instrumental limitations of these orbiters, not designed for detailed imaging of fast-moving, relatively small objects from afar, meant that while they confirmed 3I Atlas's presence, they offered no definitive answers, no sharp details, no aha moment. It was like getting a blurry photograph of a Bigfoot sighting. It confirms something was there, but tells you nothing of its true nature. The silence from NASA, however, was deafening. Speculation intensified, fueled by the stark contrast between the extraordinary nature of 3I Atlas and the complete lack of high-resolution data. In the absence of official information, the human mind abhors a vacuum, and speculation rushed in to fill the void. This was especially true after amateur astrophotographers, a global network of dedicated enthusiasts with powerful telescopes and keen eyes, began sifting through raw NavCam images from NASA's Perseverance rover on Mars. They identified an elongated streak, a peculiar smudge, that seemed to appear in the rover's field of view. While experts were quick to attribute this streak to motion blur, a common artifact when trying to photograph a fast-moving object with a fixed camera, the damage was already done. The image, however indistinct, sparked comparisons to cigar-shaped objects like Oumuamua, the first interstellar object, which had itself ignited a firestorm of alien spaceship theories. Even a blurry image in the right context can become a potent catalyst for conjecture. This perceived anomaly, coupled with the official silence, quickly birthed a narrative of a deliberate cover-up. Unverified reports began circulating, claiming that NASA had briefed certain media outlets with a pre-packaged normal comet narrative, yet failed to provide any supporting evidence from the Mars flyby. This felt disingenuous to many, a classic case of tell, don't show. Adding fuel to this already blazing fire was NASA's own checkered history. Past instances of scrubbing, controversial imagery, or withholding data had cultivated a deep-seated distrust among certain segments of the public. Whether these instances were justified scientific caution or actual suppression, the perception was clear. NASA had a precedent for being less than fully transparent. In this charged atmosphere, every delay, every lack of detail, every official pronouncement that lacked concrete evidence was interpreted as further proof of a clandestine operation. Even renowned astrophysicist Avi Loeb, a proponent of the alien artifact hypothesis for Oumuamua and a vocal commentator on 3I Atlas, weighed in on NASA's silence. However, rather than attributing it to a grand conspiracy, he offered a more grounded, yet equally frustrating explanation: terrestrial stupidity. Loeb suggested that the bureaucratic inefficiencies, the political maneuvering, the fear of missteps, and the general human failings within large institutions were more likely culprits than a shadowy cabal. This was a scathing indictment. implying that the failure to release critical data wasn't necessarily malicious, but simply the result of an organization tripping over its own feet. While perhaps less dramatic than a cover-up, it was no less infuriating for those desperate for answers. The silence, regardless of its cause, created a fertile ground for diverse and often wild theories to take root, illustrating a fundamental challenge in the age of instantaneous information. How do scientific institutions maintain credibility and trust when confronted with extraordinary events and an impatient, highly connected public? Think about a time in your own life when a lack of information led to rumors or misunderstandings. How did you feel? How important is transparency, whether from institutions or in personal relationships, when facing uncertainty? Does terrestrial stupidity resonate with your experiences, or do you tend to lean towards a more cynical view of powerful organizations? As October drew to a close, 3I Atlas continued its inexorable journey towards the heart of our solar system, approaching its perihelion, its closest point to the Sun, on October 29, 2025. This passage, however, marked a new and critical phase in the cosmic mystery. 3I Atlas entered a month-long blackout period. From Earth's perspective, it slipped behind the dazzling glare of our star, completely hidden from view. Imagine a magician's trick, where the most crucial part of the illusion happens when the subject is obscured from your sight. This was precisely the situation with 3I Atlas. This month-long blind spot was particularly significant because perihelion is when a comet should exhibit maximum activity. The Sun's intense heat would vaporize its icy components, leading to dramatic outgassing, the formation of a brilliant coma, and an extended tail. This is when a comet truly comes alive, a celestial fireworks display. But for 3I Atlas, this most active and revealing period became a black box, a time of unknowing. We were denied a direct, continuous view of its most dynamic behavior, a gaping hole in our observational record that would fuel endless speculation. Avi Loeb, ever the provocateur, seized upon this observational void. He proposed that if 3I Atlas were indeed technological, this blind spot offered a perfect opportunity for clandestine maneuvers or the deployment of smaller probes, unobserved by watchful earthbound eyes. Imagine a submarine using the cover of darkness to launch a reconnaissance drone. The retrograde orbit of 3I Atlas, meaning it was orbiting the Sun in the opposite direction to the planets, further amplified this possibility. Such an orbit facilitates multiple close planetary encounters, allowing an intelligent probe to visit different worlds without expending excessive fuel for course corrections. It's like a meticulously planned grand tour, leveraging the gravitational slingshots of planets to achieve its objectives. If this was a natural comet, the blind spot simply meant we missed some cool fireworks. If it was something else, it meant we missed everything. Adding to the tapestry of theories, Michael Salla, a proponent of more speculative exopolitics and UAP, unidentified aerial phenomena, research, introduced even more imaginative white hat and cooperative extraterrestrial hypotheses. These theories suggested that perhaps, far from being a random event, 3I Atlas's passage and the ensuing observational gaps were part of a deliberate, perhaps even benevolent plan. Could advanced extraterrestrial civilizations be orchestrating these flybys, using natural celestial mechanics to send a message or conduct observations under the cloak of our Sun? Or perhaps, as white hat theories suggest, certain hidden human factions with advanced knowledge were already aware of 3I Atlas's true nature and were strategically managing the flow of information. While these ideas reside firmly in the realm of speculation and science fiction, for most, the very existence of such theories highlights how information gaps, especially concerning extraordinary events, become fertile ground for the wildest of imaginations, pushing the boundaries of what we consider plausible. Further compounding the information void was the role of ESA's JUICE spacecraft. This intrepid probe was indeed positioned to observe 3I Atlas during its perihelion passage, providing a unique off-angle perspective that Earth-bound telescopes couldn't achieve. This was a crucial piece of the puzzle, a potential golden ticket to understanding what happened behind the sun. However, there was a catch, a delay that felt agonizingly long. JUICE wouldn't transmit its data back to Earth until February 2026. This meant that while observations were being made, the results remained locked away in a cosmic vault for months, extending the information drought and prolonging the uncertainty. The answers were out there, but they were trapped in transit. And just when it seemed the observational challenges couldn't get any worse, another critical observation window was inexplicably closed. NASA, weeks before 3I Atlas was slated to pass near Jupiter in March 2026, deactivated Juno's cameras. Juno, a spacecraft meticulously studying Jupiter and its environment, was perfectly positioned to provide unprecedented close-range imagery of 3I Atlas as it swung past the gas giant. This was a baffling decision. Why deactivate a capable instrument at such a critical juncture? Was it a budgetary constraint, a technical issue, or something more? The official explanations, if any were given, were vague, and the act itself effectively removed another potential source of invaluable, close-range imagery. The cumulative effect of these observation gaps, the government shutdown, the delayed JUICE data, and the deactivated Juno cameras, meant that any unexpected behavior from 3I Atlas, any anomaly during its most active phases, would only be known after the fact, without the benefit of continuous, high-resolution observation. We were destined to piece together a story from fragments, leaving immense room for interpretation, and perhaps for secrets to remain hidden. Think about moments in your life when you were kept in the dark about something important. How did that lack of information affect your perception or decisions? Do you believe that information, even if incomplete or delayed, is always better than outright silence? What do these patterns of obscured information tell us about institutional behavior, whether in science, government, or even personal relationships? Among the many perplexing attributes of 3I Atlas, perhaps none generated as much head-scratching and vigorous debate as its wildly inconsistent and statistically improbable size and mass estimates. It was a central puzzle, a cosmic riddle that seemed to defy the fundamental laws of probability and cometary physics. Imagine trying to weigh an elephant, but every scale gives you a drastically different reading. One says it's the size of a cat. Another says it's a small mountain. This was the dilemma with 3I Atlas. Initial ground-based estimates based on its brightness and apparent size suggested a diameter of 10 to 20 kilometers. While certainly large for a comet, this was within the realm of possibility. However, as more advanced instruments trained their sights on the object, the numbers began to fluctuate wildly. Later, more refined Hubble data, with its superior resolution, narrowed this estimate to a range of 440 meters to 5.6 kilometers. This was a significant reduction from the initial ground-based estimates, suggesting a smaller, perhaps denser object. Such discrepancies are not entirely uncommon in early observations, as astronomers refine their models and acquire better data. But then came the Sphere-X infrared observations, and with them, a bombshell that sent shockwaves through the astronomical community. Sphere-X indicated a truly colossal 46-kilometer diameter. Let that sink in for a moment. 46 kilometers. This wasn't just large, it was immense, a behemoth by cometary standards. This estimate implied an unfathomable mass exceeding 33 billion tons, a staggering figure that would make it 1,000,000 times more massive than 2I Borisov, the previous interstellar comet. To truly grasp the scale, consider that Borisov was already a substantial object. 3I Atlas, if these Sphere-X readings were accurate, was a Goliath, a cosmic leviathan beyond anything previously conceived for an interstellar wanderer. This statistical anomaly was precisely what ignited the most intense debates. How could the third interstellar object ever detected be so disproportionately gargantuan? The universe, in its grand design, generally follows power law-size distributions. There are many small objects, fewer medium-sized ones, and very, very few truly massive ones. To find such a colossal object so early in our observational history of interstellar visitors was akin to digging for gold and immediately striking a diamond the size of a house. It challenged all known power law size distributions for natural objects, making it a statistical outlier of astronomical proportions. The very rarity of detecting interstellar objects, combined with the extreme size of 3I Atlas, seemed to whisper, "This isn't random." Avi Loeb, once again, was quick to highlight this glaring discrepancy, viewing it as another potential piece of evidence for a non-natural origin. For Loeb, such an improbable size wasn't just a statistical fluke. It hinted at something engineered, something designed to be resilient and perhaps even to convey information. After all, a larger object offers more structural integrity and potentially more internal volume for technological components. Other, more conventional-minded astronomers, however, sought natural explanations to reconcile this bewildering size problem. One prominent hypothesis suggested that 3I Atlas might be a highly porous rubble pile structure. Imagine a loose conglomeration of smaller rocks and dust, held together by weak gravity, rather than a solid monolithic body. Such an object could appear large due to its volume, but its actual mass, and thus density, would be much lower. This would help to explain how such a large object could exist without violating known physical principles, allowing for a vast diameter without an impossibly high density. Another explanation posited that the Spherex infrared observations, which measure heat emitted by the object, might be picking up not just the solid nucleus, but an extended, optically thick dust envelope surrounding it. If 3I Atlas had a dense, obscuring cloud of dust or gas around it, the infrared instruments might interpret this vast envelope as the object's actual size, leading to an overestimation of its true solid nucleus. This would effectively make the elephant appear larger than it is, simply because it's cloaked in a thick, radiating fog. However, the agonizing lack of detailed images from the crucial Mars flyby meant that this fundamental question about 3I Atlas's true nature, its actual size, density, and composition, remained stubbornly unanswered. Without close-up observations to resolve its physical structure, differentiate between nucleus and coma, or precisely measure its mass through gravitational interactions, the scientific community was left to grapple with conflicting data and tantalizing hypotheses. This unresolved mystery left the door wide open for both natural and technological interpretations, each vying for supremacy in the absence of definitive visual proof. The mass problem wasn't just a detail. It was a core pillar of the entire 3I Atlas enigma, challenging our very understanding of what constitutes a normal cosmic wanderer. Have you ever encountered a situation where conflicting information or data made it impossible to get a clear picture of something important? How did you navigate that uncertainty? Does the idea of a rubble pile comet or a massive dust-shrouded object resonate more with your intuition? Or does the sheer improbability of its size make you wonder if there is more to the story? Every object in the cosmos has an origin, a birthplace that imprints it with a unique story. For 3I Atlas, tracing this origin star system proved to be an immensely challenging, almost poetic endeavor. Imagine trying to trace the footsteps of someone who has wandered for billions of years across an entire continent, with countless paths crisscrossing and fading into the sands of time. This was the task facing astronomers, as 3I Atlas carried the echoes of eons of galactic travel within its very structure. Using sophisticated computational models, scientists attempted to simulate its backward journey through time, unwinding its trajectory across the vast expanse of the Milky Way. Its high vertical velocity, a staggering 18.5 kilometers per second perpendicular to the galactic plane, provided a crucial clue. This unusually fast up and down motion, relative to the galactic disk, pointed towards an origin within the Milky Way's ancient, metal-poor, thick disk population. To understand this, picture our galaxy like a giant, shimmering pancake. Most stars, including our Sun, reside in the thinner, younger, thin disk. The thick disk is an older, more diffuse component, home to stars that formed early in the galaxy's history, before it had accumulated many heavy elements, which astronomers refer to as metals. These stars often have more eccentric orbits, plunging above and below the galactic plane. So 3I Atlas's velocity was like a cosmic accent, betraying its ancient lineage. These simulations, a form of cosmic archaeology, suggested that 3I Atlas could be astonishingly old, potentially ranging from 7.6 to a mind-boggling 14 billion years old. To put that in perspective, our own Sun is a mere 4.6 billion years old. This meant 3I Atlas could be billions of years older than our Sun, a true relic from an earlier, less chemically enriched epoch of galaxy formation. It was a time when the universe was still in its infancy, when the first stars were forging the initial heavy elements, and the building blocks of planets were fundamentally different. This ancient origin, supported by its unusual carbon dioxide-rich composition, a composition that speaks of primordial conditions, strongly implied that it was a fossil, a pristine fragment from a time before our corner of the galaxy was even fully formed. The lack of heavy elements in the early universe meant that objects forming then would have a different chemical makeup. A high carbon dioxide content could be a direct consequence of these primordial conditions, where the raw materials for comets were distinct from those found in younger star systems like our own. It was a chemical signature of deep time, a message from the galactic dawn. Despite extensive simulations, rigorously tracking its path through billions of years, no recent stellar flyby could account for 3I Atlas's current trajectory. This was a critical finding. It confirmed that this wasn't an object recently ejected from a nearby star system. Rather, it was a true wanderer, a cosmic nomad that had been traversing the interstellar medium for an unimaginable duration. It had been exposed to the harsh vacuum and relentless radiation of interstellar space for billions of years, a testament to its incredible resilience. This confirmed independence from any recent stellar system strengthens the case for common interstellar objects. If we are finding such objects, and one is incredibly ancient, it suggests that the galaxy is teeming with these cosmic vagabonds, remnants of countless star systems that have long since dispersed their planetary debris. The universe, far from being neatly compartmentalized, is a vast, interconnected web of migrating celestial bodies. The revelation of 3I Atlas as ancient origins underscores the profound gaps in our current understanding of galactic evolution and the formation of planetary systems across cosmic time. We are only just beginning to grasp the full extent of this galactic diaspora. Fortunately, the future holds promise. Upcoming systematic surveys, such as those planned by the Vera C. Rubin Observatory, with its unparalleled ability to scan vast swathes of the sky for faint, fast-moving objects, are expected to provide the statistical context currently lacking for objects like 3I Atlas. These surveys will help us understand just how common these ancient wanderers truly are, and whether 3I Atlas is an extreme outlier, or merely the first of many such venerable interstellar travelers we are yet to encounter. Until then, its origin remains a captivating tale of deep time and cosmic endurance, hinting at a universe far older and more complex than we can fully comprehend. How does knowing the potential age of 3I Atlas, billions of years older than our Sun, change your perspective on its journey? Does it make you feel more connected to the ancient history of our galaxy, or more aware of the immense timescales of cosmic phenomena? How do you think our understanding of our own planet's history might change if we could trace back the origins of its building blocks to such deep time? After a month of agonizing silence, hidden behind the blinding brilliance of our Sun, Early December 2025 heralded a pivotal moment, the re-emergence of 3I Atlas. Like a celestial actor stepping back onto the stage, it once again became observable to Earth-based telescopes. This wasn't just another observation window. It was the crucial post-perihelion phase, the time when a comet, having experienced its closest and most intense interaction with the Sun, is expected to be in its most active and therefore most revealing state. The cosmic detective story was back on. The scientific community, along with a vast global network of amateur astronomers, had been holding its breath. This wasn't merely a passive waiting game. It was a meticulously coordinated effort. Amateur astronomers, often equipped with surprisingly powerful telescopes and boundless dedication, prepared to play a critical role. They would meticulously track its brightness, monitor its precise trajectory, and most importantly, look for any signs of fragmentation. Had the intense solar radiation caused it to break apart? Had its activity dramatically increased, or perhaps unexpectedly decreased? These initial ground-based sightings, the very first glimpses after its month-long eclipse, were paramount to addressing these immediate burning questions. Compounding these Earth-based efforts, ESA's JUICE spacecraft, while its data was still months away, provided a unique advantage. Having observed 3I Atlas from a different, off-ecliptic angle between November 2nd and 25th, it held the key to crucial multi-angle data during the perihelion itself. This perspective was invaluable because what looks like one thing from Earth might appear entirely different from another vantage point in space. Imagine trying to understand a complex sculpture by only looking at it from one side. JUICE offered another dimension. While we wouldn't see this data until February 2026, the knowledge that it existed provided a powerful undercurrent of anticipation, a promise of future revelations that kept hope alive. This period vividly highlighted the indispensable importance of citizen science in filling critical information gaps, especially when institutional data is delayed or withheld. While professional observatories are powerful, they are often oversubscribed and limited by funding or political factors. The global network of amateur astronomers, with their distributed resources and passionate dedication, can provide invaluable continuous monitoring, rapidly sharing observations, and collectively building a more complete picture. In the case of 3I Atlas, their independent observations would act as an essential check and balance, providing an alternative stream of data to compare against any official pronouncements, thereby fostering transparency and countering potential narratives of secrecy. However, despite the renewed observational opportunities, a significant challenge remained. Post-perihelion observations, by their very nature, would only show the results of 3I Atlas's passage around the Sun, not the event itself. We would see the aftermath, not the action. This made it incredibly challenging to differentiate between natural cometary behavior and potential deliberate maneuvers or probe deployment. For instance, comets can exhibit a rocket effect, a non-gravitational force generated by the asymmetric outgassing of volatiles, pushing the comet slightly off its expected trajectory. This is a perfectly natural phenomenon. But how would one distinguish this from a subtle, deliberate course correction by an intelligent propulsion system? Without continuous high-resolution observation during the perihelion, the nuance would be lost, leaving room for doubt and conflicting interpretations. This required extraordinarily precise and sustained astrometry from professional observatories. Every tiny deviation from the predicted path would need to be meticulously measured and analyzed. Was it consistent with known outgassing models, or was it something else entirely? The re-emergence of 3I Atlas from the Sun's embrace was a moment of intense scrutiny, offering either a calming confirmation of conventional cometary behavior or perhaps igniting a fresh wave of intense scrutiny and reigniting the debate about its true enigmatic nature. The cosmic stage was set once more, and all eyes were on the returning star, hoping it would finally reveal its deepest secrets. Think about a situation where you've had to piece together a story from after-the-fact information. How much harder was it to draw definitive conclusions? What role do you think citizen science and amateur enthusiasts play in solving grand mysteries, whether cosmic or earthly? How does their independent spirit challenge or complement official narratives? The extraordinary nature of 3I Atlas, coupled with the frustrating observational gaps, inevitably ignited a fierce intellectual battle within the scientific community. It wasn't just about data, it was about methodology, philosophical approaches, and the very definition of scientific rigor. At the forefront of this intellectual skirmish was Jason Wright, a prominent astrophysicist who became a vocal and fierce critic of Avi Loeb's hypothesis of an alien spacecraft. Wright didn't mince words, labeling Loeb's ideas as nonsense and accusing him of motivated reasoning, a particularly cutting academic indictment. Motivated reasoning, in scientific terms, refers to the psychological phenomenon where an individual unconsciously selects a conclusion early in their investigation and then subsequently cherry-picks supporting evidence while dismissing or downplaying any contradictory data. Wright argued that Loeb, captivated by the allure of an extraterrestrial explanation, was inadvertently allowing his hypothesis to guide his interpretation of the anomalies, rather than letting the anomalies guide him to the most parsimonious, simplest explanation. It's the difference between asking, "Is this an alien spaceship?" and "What is the most plausible explanation for these observations?" Wright meticulously highlighted that, while each anomaly of 3I Atlas was intriguing, all of them, when viewed through a conventional lens, had plausible natural explanations. The forward-pointing glow, for instance, could be an unusual viewing geometry of a typical comet tail, appearing to be ahead due to our perspective, or an optical illusion. The peculiar composition could be attributed to variations in cometary formation within different interstellar environments, or even a highly unusual but natural chemical reaction. The statistical unlikeliness of its immense size, while certainly eyebrow-raising, did not equate to impossibility. The universe is vast, and extremely rare events, while improbable, do happen. 1,000,000 to 1 chance still happens once in 1,000,000 times. This public clash exposed significant tensions within the SETI, Search for Extraterrestrial Intelligence, community itself. There were genuine concerns that sensational claims, especially those lacking rigorous, undeniable evidence, could undermine the field's scientific credibility. SETI, historically, has struggled with public perception, often being conflated with fringe theories and ufology. For many mainstream scientists, the fear was that embracing unproven alien artifact hypotheses for objects like 3I Atlas or Oumuamua would drag the entire field into disrepute, making it harder to secure funding and respect for legitimate research. The worry was that if every anomaly was instantly labeled alien, it would dilute the truly groundbreaking discoveries and obscure the rigorous scientific process. Loeb, on the other hand, presented himself as a modern-day Galileo-esque figure, challenging what he perceived as scientific orthodoxy and intellectual stagnation. He argued that the scientific community, particularly in astrobiology and SETI, was too conservative, too fearful of venturing beyond established paradigms. He believed that dismissing anomalies out of hand, simply because they challenge conventional wisdom, was an anti-scientific stance. For Loeb, the extraordinary nature of the observations warranted extraordinary consideration, and the unwillingness to seriously consider a technological origin was a failure of scientific imagination. He saw himself as pushing the boundaries, forcing science to confront uncomfortable possibilities. At the core of this intense debate lay the principle of Occam's razor, the philosophical tool that suggests, among competing hypotheses, the one with the fewest assumptions should be selected. Most astronomers, adhering to this principle, favored the simpler natural comet hypothesis for 3I Atlas. It required fewer assumptions, mainly that current cometary models could be stretched to accommodate unusual variations. Compared to the complex web of assumptions required for an alien civilization to engineer, launch, and precisely steer such an object through our solar system. For them, the natural explanation, even if unusual, was the path of least resistance. Loeb, however, countered that such reasoning implicitly made a critical and unprovable assumption, that the prior probabilities for alien civilizations are unknowable, or so infinitesimally small that they effectively rule out a technological origin by default. He argued that if intelligent life is common in the universe, then the prior probability of encountering an alien artifact might not be as low as some assume. He challenged the very foundation of Occam's razor in this context, suggesting that by prejudging the likelihood of alien life, we might be blinding ourselves to its actual presence. The scientific battleground wasn't just about Three-Eye Atlas. It was a deeper philosophical struggle about how science should approach truly novel and potentially paradigm-shifting observations, and how open-minded it should be to explanations that lie beyond our current understanding. Where do you stand in this scientific debate? Are you more inclined to favor Occam's razor and natural explanations? Or do you believe that sometimes the simplest explanation isn't always the correct one, especially when dealing with the unknown? How important is it for scientists to challenge orthodoxy, even if their ideas are initially met with skepticism or ridicule? As the scientific debate raged within academic circles, a far more chaotic and widespread storm erupted across the digital landscape. Three-Eye Atlas didn't just capture the attention of astronomers. It ignited a massive social media frenzy, transforming platforms like X, formerly Twitter, Reddit, YouTube, and TikTok into veritable battlegrounds for information, speculation, and, unfortunately, an avalanche of misinformation. In an era of instant communication, a cosmic anomaly quickly becomes a cultural phenomenon, amplifying every whisper and turning. While some corners of the internet fostered genuinely insightful discussions grounded in scientific observations, many quickly veered into the speculative abyss. The vacuum of definitive information from official sources, as discussed in previous chapters, proved to be an irresistible magnet for unsubstantiated claims. Forums and comment sections exploded with theories ranging from Three-Eye Atlas being a gargantuan alien mothership on a reconnaissance mission to a harbinger of imminent doom, an extraterrestrial weapon aimed at Earth. Each anomaly, each unanswered question, was seized upon as definitive proof for the most sensational narrative. The perceived forward glow, clearly a propulsion system. The massive size, a fully equipped interstellar vessel. The silence from NASA, a government cover-up to prevent mass panic. The speed at which misinformation propagated was staggering. Manipulated screenshots, doctored images, and false quotes attributed to respected scientists like Michio Kaku went viral, reaching millions of users before any fact-checking could even begin. These instances starkly highlighted the profound challenge of fact-checking in an algorithm-driven environment, where sensationalism often trumps accuracy. Algorithms, designed to maximize engagement, inadvertently amplified the most outlandish and emotionally charged content, regardless of its veracity. A meticulously researched scientific explanation, with its caveats and nuances, simply couldn't compete with a punchy, confident yet entirely false claim of an alien invasion. A particularly insidious aspect of this social media storm was how the absence of evidence was frequently reinterpreted as evidence of a cover-up. "They're not showing us the pictures because it's too terrifying," became a common refrain. This created a self-sealing logic where conspiracy theories became unfalsifiable. Any lack of official data simply proved the conspiracy, and any official data that was released was dismissed as disinformation or a planted narrative. The very nature of the platforms, with their echo chambers and confirmation bias, entrenched these beliefs, making it incredibly difficult for scientists and institutions to break through the noise with accurate evidence-based information. Adding another layer of complexity, memes and satirical content further blurred the lines between humor and misinformation. While often intended as harmless jokes, these viral snippets, stripped of context, could easily be misinterpreted as factual statements by those less discerning or unfamiliar with the underlying science. The playful banter around Space Peanut, a nod to Oumuamua's shape, or Atlas the Alien Ark, contributed to a collective narrative that, while entertaining, often obscured the serious scientific questions at hand. This chaotic information landscape presented significant, almost insurmountable challenges for scientists and institutions genuinely trying to communicate accurate information. Their nuanced explanations, the measured caution inherent in the scientific process, and their appeals for patience were often drowned out by the sheer volume of confident, yet often demonstrably false, definitive claims. The public, bombarded with contradictory information, struggled to discern truth from fiction, and trust in authoritative sources was further eroded. The social media storm around 3i Atlas wasn't just a side effect. It became an integral part of the event itself, shaping public perception, influencing scientific discourse, and highlighting the urgent need for critical thinking and media literacy in a hyper-connected world. It showed us that in the digital age, a cosmic enigma can quickly become a mirror reflecting our own societal anxieties, biases, and desires for the spectacular. Thinking about the information you consume daily, how do you personally verify what's true, especially when faced with conflicting reports? Have you ever found yourself caught in an online echo chamber? And if so, how did you become aware of it? What responsibility do social media platforms have in curbing the spread of misinformation during events like the 3i Atlas phenomenon? The emergence of 3i Atlas from its month-long concealment behind the Sun in early December 2025 was more than just an astronomical event. It was a pivotal moment of collective anticipation, a global exhale after holding breath for weeks. This was the moment when the cosmic detective story, temporarily paused, resumed with renewed urgency. The first ground-based sightings, facilitated by the tireless efforts of amateur astronomers coordinating globally with professional observatories, immediately began to address some of the most pressing questions that had festered during the solar blackout. The initial observations were crucial for two primary reasons. Firstly, observers desperately wanted to know, was it intact or fragmented? The intense heat and radiation of perihelion can cause comets, especially those with unusual compositions or fragile structures, to break apart. A fragmented object would offer different clues about its internal composition and resilience, potentially supporting a rubble pile hypothesis or revealing internal structures. Conversely, if it remained intact, it would speak volumes about its structural integrity, possibly bolstering arguments for a more robust or even engineered nature. Tracking any pieces would be critical, while natural breakup is the more likely scenario, distinguishing between a chaotic fragmentation and a more deliberate, organized separation of components, perhaps the deployment of probes, would require meticulous observation. Secondly, a major concern was its brightness. Had it changed dramatically? A significant increase in brightness would indicate massive outgassing, consistent with an active comet. A stable or even reduced brightness might suggest something else entirely. Had its composition shifted, or had it simply exhausted its most volatile materials? These visual cues were the first direct post-perihelion data points, offering either immediate confirmation of conventional comet behavior or sparking further intense scrutiny and concern about anomalies. The collective effort of amateur astronomers, with their distributed geographical coverage, was instrumental in building a continuous observational record, capturing every fleeting glimpse as 3i Atlas moved across the night sky. Beyond visual confirmation, trajectory analysis became paramount. distinguishing between non-gravitational forces from outgassing, the well-understood rocket effect, where escaping gas acts as a tiny thruster, and any unexplained deviations that might suggest other influences, such as a propulsion system, required an exquisite level of precision. Astronomers would compare its post-perihelion path against gravitational predictions and models incorporating natural outgassing. Even subtle, persistent deviations, if not attributable to known cometary physics, would raise red flags. This wasn't merely about finding an object. It was about understanding its motion with unprecedented accuracy, interpreting every twitch and turn in its cosmic dance. While these initial December observations were providing invaluable, real-time insights, the more detailed perihelion data from ESA's JUICE spacecraft remained tantalizingly out of reach, scheduled for transmission in February 2026. This meant that the full, high-resolution picture of what happened during 3I Atlas's most dynamic phase was still months away. The December emergence, therefore, served as a vital bridge, offering the first post-perihelion clues and either reinforcing the conventional narrative or deepening the mystery further. It was a crucial, anxious waiting game, where every photon collected from the returning object carried the potential for revelation or continued bewilderment. The world watched, telescopes poised, as 3I Atlas emerged from the sun's fiery embrace, ready to tell its next chapter. Imagine you are one of the astronomers. What specific piece of information from 3I Atlas's re-emergence would you be most eager to obtain? And why? How does the human desire for immediate answers clash with the slow, meticulous process of scientific discovery, especially when there's so much at stake? The saga of 3I Atlas, following in the enigmatic footsteps of Oumuamua and Borisov, solidified a distinct pattern in our nascent understanding of interstellar objects. Each discovery, a rare glimpse into the galaxy beyond our solar system, invariably sparked intense debate not just about their origins, whether natural or artificial, but also highlighted persistent and troubling issues of information control, scientific communication, and public trust. These interstellar visitors aren't just cosmic curiosities. They are litmus tests for how humanity grapples with the truly unknown. The U.S. government shutdown, silencing NASA's critical Mars flyby data at the most crucial juncture, created more than just an information void. It fostered a powerful perception of deliberate withholding. This erosion of public trust, fueled by an absence of transparency and a perceived lack of accountability, mirrored historical instances of government secrecy regarding space observations, from the face on Mars to various UFO phenomena. When official channels go dark, the public naturally seeks answers elsewhere, often finding them in the realm of speculation and conspiracy. This tension between scientific caution, which demands careful calibration, peer review, and verification before public release, and the public's understandable demand for immediate, unfiltered transparency, reached a boiling point with 3I Atlas. This clash was exacerbated, almost weaponized, by the pervasive influence of social media. The scientific community's rigorous, yet inherently slower process of data analysis, publication, and peer review simply could not compete with the rapid-fire, often unverified claims spreading instantly online. Nuance was lost, context was stripped away, and thoughtful skepticism was often mistaken for a cover-up. The scientific method, designed for precision and truth, found itself struggling in a landscape that prioritized speed and sensationalism. The story of 3I Atlas, therefore, serves as a profound and urgent test case. It forces a critical re-evaluation of how science communicates with a public that increasingly demands direct access to raw data and harbors a deep-seated suspicion of authority. In an era of distributed information, where anyone can become a broadcaster, the old models of scientific dissemination are no longer sufficient. Scientists must become better communicators, more engaging storytellers, and more proactive in addressing speculation without dismissing legitimate public curiosity. Institutions must rebuild trust by embracing radical transparency, even when the answers are incomplete or uncertain. Ultimately, 3i Atlas isn't just about a potential alien artifact or a rare comet. It's about us. It's about our capacity to confront the unknown with open minds and rigorous inquiry, rather than succumbing to fear or dogma. It's about the delicate balance between scientific integrity and public engagement. And it's about the enduring human quest to understand our place in a universe that continues to surprise us, to challenge our assumptions, and to whisper secrets from across unimaginable distances. What do you think 3i Atlas truly is? Do you believe the universe is teeming with intelligent life? Or are we, for now, truly alone? Share your thoughts in the comments below. Thank you for joining me on this incredible cosmic journey. I hope you found this exploration of 3i Atlas both thought-provoking and inspiring. Stay curious, stay questioning, and keep looking up. I wish you good health and clear skies. If you enjoyed this deep dive, please consider subscribing to the channel for more fascinating stories from the cosmos.